I want you to imagine a material. On the surface, it just looks like a simple white powder, but inside, it's holding a secret that honestly sounds like it's straight out of science fiction. Today, we're going to dive into the story of that very material, a Nobel Prize-winning wonder that could seriously change our world. To really wrap your head around this, let's start with something super simple, something you see every day. Just picture a single spoonful of this white, crystal-like powder. That's it. Got that image in your mind? Good. Okay, now here is where your mind is going to be blown. If you could take that single spoonful of powder and unfold all of the surfaces tucked away inside it, it would cover an entire football field. I'm not kidding. This isn't magic, it's a molecular marvel, and it's packed with an absolutely unbelievable amount of empty space. So what can you do with all that space? Well, you can do some pretty incredible things. This stuff is so thirsty, it can literally suck drinkable water right out of the air in the driest deserts on Earth. It can also act like a molecular cage for pollution. I mean, you can design its internal structure to perfectly trap carbon dioxide molecules as they come out of industrial smokestacks. It's a way to fight climate change right at the source. And it can clean our water. It's capable of catching some of the nastiest, most stubborn pollutants out there, those toxic forever chemicals. Now, I know this sounds like science fiction, but it's not. In fact, the revolutionary science behind this material is exactly what just won the 2025 Nobel Prize in Chemistry. So who are the master builders who designed this seemingly impossible material? Well, let's meet the architects who actually turned this chemical dream into a reality. The Nobel Prize was awarded jointly to these three pioneering chemists, Richard Robson, Susumu Kitagawa, and Omar Yaghi. They were honored for creating a completely new class of materials. And you don't have to take my word for it. The Nobel Committee put it perfectly. They were honored, and I quote, for the development of a completely new kind of molecular architecture. And this isn't just some lab curiosity, it's a tool specifically designed to help us solve some of the biggest challenges we face as a species. Okay, so what is this new architecture, really? To understand it, we need to zoom in, way in, and look at the invisible building blocks that make it all possible. This material is called a metal organic framework, or MOF for short. And at its core, it's basically a microscopic 3D grid, a crystal that's mostly just empty space, made up of these tiny, perfectly arranged pores. Honestly, the best way to think of it is like a sponge, but on a molecular scale. So how do you even make one? Well, this is the wild part. Imagine a construction set that builds itself. You start with metal ions. Think of these as the joints or corners of a building. Then you add organic molecules, which are like the long rods or beams that connect those joints. You just mix them together in a solution and, incredibly, they just snap together all on their own, self-assembling into a perfect crystal grid. And just like that, a molecular sponge is born. But of course, an idea this revolutionary doesn't just appear out of nowhere. It was a scientific journey, a story built piece by piece over decades by our three Nobel laureates. So the story really kicks off in 1989. That's when Richard Robson first discovered that these metal and organic pieces could actually self-assemble into these open, grid-like structures. A little bit later, Susumu Kitagawa came along and showed that these frameworks weren't just rigid cages. They could be flexible. They could expand and contract, almost like they were breathing. And then, in the 1990s, Omar Yaghi completely mastered the design process with something he called reticular chemistry. Think of it like chemistry with Legos, using rigid building blocks to design super strong, predictable structures. This is what allowed scientists to intentionally build incredibly stable MLFs with those record-breaking football field-sized surface areas. So, we've got these incredible, customizable super sponges. Now for the most exciting part. What can we actually do with them? How can they help humanity? We hinted at a few of them in the beginning, but let's really dig into the superpowers this technology unlocks. What can these molecular sponges really do? Well, because you can precisely tune the size and shape of the pores, you can design a MOF for almost any job. You need to capture carbon dioxide? You design a MOF with pores that are the perfect size to grab it. Need to pull water molecules from thin air? Yep, there's a MOF for that. They can act as these ultra-safe storage tanks for clean fuels like hydrogen, or they can be used as microscopic nets to pull those harmful forever chemicals right out of our drinking water. And honestly, the possibilities are nearly endless. This is why this discovery is so profound. It really is about more than just a new material. It represents a whole new way of thinking, a way to design and build matter atom by atom, just like an architect designs a building. You're carefully deciding not just what it's made of, but exactly where you want to leave the empty space for all this amazing chemistry to happen. So, the final and probably most important takeaway is this. At the molecular scale, empty space isn't nothing. It's a powerful and versatile tool that we can use to filter, to store, to capture, and to transform our world for the better. So, I'll leave you with this question. Looking at all of its potential, which application of this incredible tool do you find the most exciting for our future?